start.
You are welcome, class. How are you all? We are fine, sir. Thank you. You are welcome to Salatif class. Today, we shall be looking at Charles Law. There's a French inventor and mathematician who promulgated a law of gas. His full name is Jacques Charles. The law of gas, or Charles Law. Today we shall look at what the law says. Now the lesson, before we start the lesson, you must be in group. Group 1 is here. Group 2, Group 3, Group 4. Thank you. Now, the first thing is to look at the first objective of the lesson is we are going to state the Charles Law, to demonstrate an activity to prove this law, and we apply the law to solve at least 3 questions. Before we continue, we are already in our group. We look at what we learned previously pertaining to kinetic theory of gases. Now, in your groups, write down at least 2 characteristics of kinetic theory of gas. What does gas say? Quickly, yes, I give you 20 seconds. Everybody write something down in your group. Okay. Group 1, what do you have? Yes? Yeah, good. Gases are high kinetic energy versus move apart. Group 2. Very good. Gases are highly compressible. They can be expanded before the shape of their container. Anybody? Yes, group 3. Yes. Very good. They have no thermonuclear forces binding them, so they move apart very well, unlike solid. Yes, my friend Joseph. Very good. They can occupy volume of any container. Now let's look at ideal solution. This is the characteristic we learned about last week. The particles they interact, there's collision between them, and the gas particle, there are no thermonuclear forces holding the particles together. We also learned that the kinetic theory of gas is seek to explain the behavior of gases in general with respect to volume, pressure, and what? Temperature. So in a nutshell, the assumption is that it used to explain how gases can be compressible. If gases can be compressible, we shall look at effects of temperature on a gas, effects of pressure on a gas, and effects of volume as well. Now, we are going to look at a simulation that explains this very, very accurately. This is a container, this is the temperature, this is the pressure, and these 3 quantities, we shall hold one constant. So we are going to hold the pressure with respect to Charles and see what will happen to temperature and the volume of the gas. So I'm going to introduce some particles. I'm introducing some particles, 300 particles.
Wow.
Can you all see the particles? What is happening here? There is massive collision going on. The more the collision, the more pressure builds up. So you can see the pressure is moving. If I introduce more, the pressure will move. Can you see increase in pressure? As the pressure is increasing, the more the particles, the more the collision, the more pressure increases. Move from here to that place. Can you see that? Let me reverse the particles and see. Is the pressure coming down?
Yes.
Pressure is coming down. Can you see that?
Yes.
So let's increase it and see what will happen. See, it has increased. So the nutshell, let's equalize it now. So there's much pressure inside. Now, with respect to Charles' law, let's hold the pressure. I'm going to make the pressure constant, meaning pressure in the gas will no more increase. Let's introduce heat. What will happen to the particles? The pressure can no more move. So what will happen? Can you see the increase in the volume? Yes. Can you see that? Yes. Can you see the volume is increasing? Yes. Let me reduce it. Meaning I'm putting ice. I'll introduce ice inside, decreasing temperature. Can you see it's coming down? Yes. So the value of temperature here is coming down. Can you see that? Yes. It's coming down. Let's increase it again. Can you see the temperature? Yes. The temperature is going up. Can you see that? Yes. So we can see that there is relation between pressure, temperature, and volume, isn't it? Yes. So, having understood this, let's go to another activity. We are going to provide with this material. We are going to look at the balloon, beaker, and hot water. Let's go. No. Come on. This is the hot water. You see the size of this balloon? Yes. We are going to measure the circumference of this balloon. We shall drop it in this hot water and see whether there will be increase in the volume of the balloon with respect to temperature. So I captured it. This is the size. Is the size. What is the volume? So we drop it here from 0. You can see it's about 23 centimeters. 25 centimeters. 25 centimeters. Now let's drop it into the hot water and see what will happen. Let me reduce the mass of the water.
Yes. It's reduced.
Let it go so that the balloon can well submerge inside the water.
Yes.
Okay, I'll hold it for just some 2 or 3 minutes and see whether there will be increase in the size of the balloon. Can you observe increase in the balloon? Can you observe it? Science deals with verification, experimentation, and observation. If you are appreciating science.
Yes.
Now I think it's enough. Let's now measure the size of this balloon as we did. 20. Okay, I drop it here. Now you can see there is an increase. No.
Initially there was a mistake. It was 20, it wasn't 25.
Yeah, initially it was 20. Yes, initially it was 20. So 20 against 21.3.
Oh yeah.
We drop it once again into ice water. Ice water is whether the size will come down. We leave it for the same time, about 60 seconds, which is exactly 1 minute. See what will happen. I think it's enough. It's time. We measure it again and see the circumference. Exactly here. It has come down to 19.1. 19.1. Okay. 19.1. So, thank you so much. You can see the difference. Hot water, the volume moves, volume was not. Now, with this analysis, what can you deduce? What can you deduce from relation between volume, temperature, and pressure? Yes, Joseph.
The higher the temperature, the higher the volume, the higher the volume of the water, the greater the volume of the substance.
Okay, yes, say.
Sir, heat increases the volume of substance.
Clap for her now. Clap. Exactly. You can observe that there is a relation between volume and what? The temperature, isn't it?
Yes.
When the temperature increases, volume increase, temperature also what? Increase. And when it decrease, volume does what? Decrease. Now, let's look at mathematical version of this. So, we can say that a Charles law at a fixed mass of gas at constant pressure, volume is directly proportional to absolute temperature. Since temperature is kept constant, it undergo when a pressure is kept constant, we call it isobaric process. Everybody, isobaric. Isobaric process. Everybody. Isobaric process. Yes, this means that the pressure is kept constant and remain unchanged. Now, let's look at it. So what we did was V directly proportional to T. There's constant of proportionality. You find this K, you are going to get V over T, isn't it?
Yes.
If you compare two objects together, it will be V1 over T1, V2 over what? T2. And if you plot a graph in temperature against volume, we are going to get a straight direct graph like this. This is how your graph is. This is on a Celsius scale, this is on a Kelvin scale, the two thermometric thermometers. Now, let's solve this problem. Everybody take your piece of paper, let's try this way. If you note, a fixed mass of gas are this, 88 cm cube, a temperature 50 degrees Celsius, is heated at a constant pressure, calculate the new volume. You do that, I give you 2 minutes to 3 minutes. Try it, let me see, to be your answer. Okay, some of you are finished already?
Yes.
You are finished? Yes. Take get your answers. Whether you are answer for this. If your answer, how many of you got this are correct? Number 1, see by hand. Good. Number 2, don't see by hand. Go, clap. Thank you. Now, we are going to mean that the lesson you understood the lesson very well. Now, we are going to try this as our final conclusion, our conclusion to the lesson. We are going to plot a graph using these values. This is volume increase. These are various volume given. This is the temperature at Celsius scale.
We are more than 15 minutes.
You plot a graph. So when we meet tomorrow, every group is going to do presentation. You present your work, and we shall analyze it, and we do the necessary correction before we move on to the next topic. So thank you so much. Thank you for coming. Thank you.